I've been doing a lot of matrix transformations in 2D and 3D, and this has been for my OpenGL graphics programming journey. And when I originally wanted to start learning graphics programming, I knew I had to learn linear algebra. So I went through a linear algebra textbook, and most of it at the beginning was Gaussian elimination practice. So I was basically solving a bunch of linear equations, and I then learned that in graphics programming, you're mostly going to be doing the matrix transformations. And I thought that I ended up wasting my time filling up a notebook full of Gaussian elimination practice. But it turns out that matrix transformation and Gaussian elimination is actually very related, and they're essentially describing the same systems, but at a different point of view. So I kind of want to just go through why exactly that is. So I have a little grid here. I have two grids actually, and they're just two-dimensional, just X and Y axis. And one's going to be the matrix transformation on the top, and the other is going to be the linear systems little grid that I have. And this is the linear system that I have here. So we want to know exactly why these two are related and what exactly the relationship is. And if I want to look at the matrix vector, or matrix transformation, sorry, we have our basis vector, and that is the one, we just have a arrow going in the x direction and then an arrow going in the y direction. So that's 1, 0 and 0, 1. Now, usually how it works with matrix transformations is we start with the basis vector, and then we have some other vector that we have as the input, and then we apply the transformation, and then we want to see how that transformation caused the change in that initial input vector to where it lands on the output vector. So right here, I'll just make a little arrow. That's actually our input vector. And the cool thing is that when you're doing linear systems or Gaussian elimination, the unknown is actually the input vector. So in the Gaussian elimination, you're essentially solving the system in reverse. So they give you the output vector here. So that's what we're finding when we want to apply the transformation in the matrix transformation view. So that's the output vector. So let me just kind of write that down. So this is input and output, and then this is the transformation. So the transformation is actually given to us in the linear systems. It's actually this little block right here. That's what gives us the numbers up here. And so when you take the input vector, and originally in the linear system, we don't have the input vector. So how we find that is actually by solving the linear system. So we do the Gaussian elimination stuff. I won't go through the Gaussian elimination because that's not really in the scope of this video, but it's just applying the negative half of the first term and then adding that to the second term and then solving for that. And then you get the y and the z. So the x is 2 and the y is 3. And so we're given the transformation that is being applied, so that's right up here. So when you end up doing the actual math of it, if we want to go through that quickly, so 2 times 2, and then 2 times 1 plus 3 times 3, and then this down term here, 3 Oop, yeah, there we go. 3 times negative 1. So after we do that, we just get 4 plus 9, and then 2 plus negative 3. And that's what gives us our output vector here. There we go. So if we want to plot that, we have the input vector that we're going to put, right here. So that's what it looks like in the initial basis vector view. So that's the input. And then when we apply this transformation, then those basis vectors are going to be where those coordinates are, and then the output vector is going to be somewhere right here, if you can imagine that. So we have those essentially. So we're saying it's essentially being solved in reverse. And then what we want to kind of connect is, what are we looking at in terms of the linear system side? Because this is going to be an actual, in the linear system side, we're actually looking at the intercept. So we're taking the first term and we're essentially drawing it as a line. And then we're going to take the second term and then we're going to be drawing that as a line. And then we want to see where those two intersect. And that intersection is actually the input vector that we're finding right here. So if we want to actually see that, we can solve for y. So we're going to solve for y on both of the terms here, and that's what gives us this little equation that we're just going to be plugging x values into. So this one right here is for the top one over here, and this little second one down here is for this one. So we're just finding y, plugging in different x values. So these are the coordinates that we get from plugging 2, 5, 8 as x. And then we get, for xy, we get 2, 3, 5, 1, 8, negative 1. And then for the other one, when we plug in 2, 1, 3 as x values, we get 2, 3, 1, 2, and 3, 4. So if we want to see those actually getting plotted, so I'll start with the first one. So we got a point there, and then 1, 2, 3, 4, 1, 2, 3, 4, 5. And then, so that goes right here. 5, 1. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 and negative 1. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. So that's one line that we have. And then when we want to see where the specific intersect is, we do the next one. So we have 2 and 3. Yep. So that's the intersect point. And then for 1, it's 1 and then 2. And then for 3, so 3 and 4. There we go. And then we just plot that. So yeah, now we can actually visualize the intersection, and where it's intersecting is exactly where the input vector is supposed to be. So that's essentially showing us exactly how these are related. And it was actually pretty cool when I first kind of figured this out, because I learned that I didn't waste my time learning this. So yeah, that's about it. I hope you guys enjoyed it.